Good afternoon. Today we're going to do a short section of notes for Chapter 6, Section 4, Solving for Imaginary Roots. Now we actually already went over how to solve for imaginary roots using completing the square. Today we're going to talk a bit about where the imaginary roots come from so that you understand their role in what we're learning. Then we'll do an example using the quadratic formula. So basically the origin of imaginary numbers was this dilemma. When x squared equals 1, we know that x has to be either 1 times 1 or negative 1 times negative 1, which is why we get two answers for x. The problem in solving becomes, what do we do if it's x squared equals negative 1? Because obviously a positive 1 times a negative 1 would mean that these x's were different, but they're not. Negative 1 times a negative 1 is a positive. 1 times 1 is a positive. So this is the situation that they used to invent imaginary numbers. They said, let's say italicized I is actually equal to the square root of negative 1. If that was the case, then I squared would be negative 1. Now you might ask, well, why in the world did they invent an imaginary unit if it doesn't really exist? It's not measurable. Well, what they found is that even though imaginary numbers and real numbers are completely different sets of numbers in the grand scheme of things, what they found is sometimes when you start with a problem, you go to imaginary, and then you use regular algebra, nothing special. Sometimes you'll end up with a real answer. And that's where imaginaries started gaining a foothold, which is there are some things we can do with imaginaries that end up with real answers. That's where it comes from. All right, so let's do an example. We're going to use the quadratic formula. If you haven't memorized the quadratic formula yet, you really need to do that. Quadratic formula can be used in a situation where ax squared plus bx plus c equals 0. A can't be 0. B and c can be, but not a. If there's no x squared, it wouldn't be a quadratic. And then your magic formula, x equals negative 1 times b plus and minus the square root of b squared minus 4ac all over 2a. All right, so the problem we're going to solve using the quadratic formula is 2x squared minus x plus 5 equals 0. Now you could use quadratic formula to find the intercepts of a parabola. It's interchangeable with completing the square. Okay, so a is 2, b is negative 1, c is 5. So x equals negative 1 times b, which is also negative 1, plus and minus the square root of negative 1 squared minus 4 times 2 times 5 all over 2 times 2. As we've talked about before, you can simplify the front and the bottom number. 1 times 1 is 1. On the bottom, 2 times 2 is 4. But it's inside this radical that you have to be a little bit careful. Exponent first, so you get a positive 1. And negative 4 times 2 is negative 8, times 5 is negative 40. So your first hint that you're going to have an imaginary number is the fact that you have a negative under the radical. When that happens, you want to immediately replace it with I. Now, what is the math that does that? Well, keep in mind that the rules of radicals say that you can separate two numbers from each other into separate radicals. So when we do that, we get a radical negative 1 times a radical 39. That's why we replace the radical negative 1 with I, and it sits outside of the radical 39. So 1 plus and minus radical 39 with I on the outside, all over 4. Now remember, standard form of an imaginary number is a plus bi. The real number comes first, the imaginary number comes second, and I is on the side. So this is actually, and you're going to have to separate that 4. 1/4 plus and minus radical 39 fourths, I on the side, comma 0 if you're required to write intercepts. If this fraction here reduces, you need to reduce it. Most of the time it won't, but if it does, you need to simplify. 39 is 13 times 3, so that doesn't need to be simplified any further. And there you have your roots. Now, technically, roots are solutions to the algebra, whereas intercepts are graphical. But we'll go over that later. Have a good afternoon.